Section 2.5a, the fundamental theorem of algebra. Fundamental theorem of algebra we've already really brought up in the previous sections. We know that a polynomial of degree n has exactly n solutions. Up until this point, we have found only real solutions of the polynomial function. Now, because we have worked with imaginary and complex numbers, we can find all solutions. If a plus bi is a solution, then a minus bi is also a solution. So we know that if we have one complex solution, we have to have a second, because complex solutions always come in conjugate pairs. So it is impossible to have an odd number of complex solutions. They always come in pairs, or an even number of complex solutions, which is why back when we did Descartes' rule of signs, we counted the number of sign changes or subtracted an even integer, because the possibilities would be, if they were imaginary, they must come in pairs, which is why we subtracted 2 each time to get all the different possibilities for real zeros. Find all zeros, write the polynomial in fully factored form. Once again, we know that real zeros correspond to x-intercepts. So in general, in equations that are of less degree than degree 3, we know that we can plug in 0 for y, solve the equation, and that will give us the solutions, because real solutions are the same as x-intercepts. So in this case, our solution, or our 0, is x equals 2. This polynomial in fully factored form, what factor produces a solution of 2? Well, it's just our original polynomial, x minus 2. Letter B, do the same thing. Plug in 0 for y. Quadratic equation now. We can factor or use the quadratic formula. This is factorable. We can set each of those factors equal to 0. And we can see we're going to get the same solution from each factor, x equals 3. And we know that x equals 3 was a solution twice. So remember, we could say that this has a multiplicity of 2. This polynomial written in fully factored form then, 3 was a solution twice. So we're going to have 2 factors, x minus 3 times x minus 3. Letter C, same thing. Find all zeros, write the polynomial in fully factored form. Well, this polynomial right off the bat here is factorable. We can pull an x out of everything. So let's go ahead and plug in 0. As we do that, I'm going to take an x out. So we're left with x squared plus 4. Once we have a polynomial that is factored and it's equal to 0, we can take each factor and set it equal to 0. There's our first solution at 0. Let's solve this second one. Normally, we would stop right there. We would say that these two solutions are not real, but now we are finding all zeros, not just real zeros. So we need to go ahead and finish this. Take the square root of both sides. We get plus or minus 2i. So our three solutions are x equals 0 and plus or minus 2i. This polynomial written in fully factored form would be f of x equals, and now write each of the factors. What factor produces a solution of 0? That's x. 2i is x minus 2i, and negative 2i is x plus 2i. There's the three factors. So now that we are finding all zeros, if you are asked to find all zeros, you better have the same number of solutions as what you do degree a polynomial. In this case, we had a degree 3 polynomial. We had 3 solutions. That also should correspond to how many factors you have. In this case, we have 1, 2, 3 factors of the polynomial. Find all zeros, write the polynomial in fully factored form. Okay, so we're doing the same thing here in D. Once again, if we plug in 0 for y, we're dealing with a polynomial that's factorable. Difference of two squares, x squared minus 1, x squared plus 1. Set each of those two factors equal to 0. Solve each one. We get x squared equals 1. So plus or minus 1. We get x squared equals negative 1. So plus or minus I. There are our 4 solutions. Fully factored form, this polynomial would be x plus 1 times x minus 1 times x plus I times x minus I. Okay, last one here. Find all zeros, write the polynomial as a product of linear factors. Notice the difference in directions. This time it says write the polynomial as a product of linear factors. That's exactly what we've been doing back here. Okay, anytime you are writing it in fully factored form, product of linear factors, you should have as many factors as you do degree of the polynomial. In this case, 4 factors, 4 solutions because it was a degree 4 polynomial. Now here, if we go ahead and we plug in 0 for y, obviously we don't know how to factor something that is degree 5. So what do? Well, this is why we have a graphing calculator. This is a degree 5 polynomial. If you remember back earlier in the chapter when we were finding only real zeros, we find as many zeros as is necessary with the calculator so that when we synthetically divide, we reduce this to a quadratic equation. In this case, we know we need to find 5 total solutions or 5 total zeros. 3 of them we are going to find with the calculator. When I synthetically divide 3 times, we will take this from degree 5 down to degree 2, in which we can then factor or use the quadratic formula to finish solving. So we're going to go ahead and put this function into the calculator right away. Y equals x to the 5th plus x cubed plus 2x squared minus 12x plus 8. All right, from this graph, let me center this a little bit better here so we get a little better picture. From this graph, we can see that we have a cross of the x-axis here, and it looks like a touch here. So we see that negative 2 is a solution and positive 1 is a solution. If you want to go ahead and calculate those with the calculator, you can. But remember, you have to synthetically divide by them anyways, which is going to prove whether or not that is crossing at those nice integer values. So I'm just going to go ahead and begin our synthetic division process. Negative 2 is the first solution that I'm going to divide by. Don't forget when you synthetically divide, you need to put in 0 for your x to the 4th term, which is not represented here. Any term that is missing in descending order, remember, you must put in a 0 to hold that position. Bring down the 1 and begin your synthetic division. Remainder of 0 shows that indeed negative 2 is a solution. Our graph came down and touched at 1, so we know 1 is a solution. Let's show that that is. Remainder of 0. We've went now from a degree 5 polynomial up here to degree 4 right here to degree 3 right here, so we still don't have it down to a quadratic. We have no other intercepts, though, that are shown on our graph, so what do we do from here? Well, if you remember back to when we were doing real zeros and we were talking about our graphs and we were talking about whether it was a cross or a touch. Remember, touch points indicated that that value was a solution more than once, an even powered factor that produced less solutions. So that means that 1 is a solution here again, because that was a touch point on our graph. Bring down the 1. Again, remainder of 0 shows that 1 is indeed a solution a second time. Now we have it reduced to a quadratic. X squared plus 0x plus 4 equals 0. solve, take the square root of both sides, and we get plus or minus 2i. So the zeros of this function are x equals -2, 1, plus or minus 2i, and we know that 1 has a multiplicity of 2. So there are all the zeros. Again, your total number of zeros should match up with the degree of the polynomial. In this case, it's degree 5. We have 1, 2, 3, 4, 5 solutions because 1 has a multiplicity of 2. So this polynomial in fully factored form, f of x equals x plus 2 produces our solution of -2. X minus 1 and x minus 1 gives us our multiplicity of 2 for our solution at 1. And x plus 2i and x minus 2i. There's our 5 linear factors for this polynomial.